Hello everyone, my name is Walid Qsia. I am a PhD student at the Higher Institute of Management of Tunis, based in Tunisia, and in this video I'm going to do a presentation about the article with the following title. The outline is as follows. First, in the introduction, we are going to see the main problem, which is the main cause that made us focus on tuning hyperparameters on imbalanced medical data. Once we have obtained our input data, we are going to apply upon them two classification algorithms. In the second section, we are going to see both of these classifiers, namely SVM and LASVM, and we will justify their choice. Next, we are going to attribute to a set of hyperparameters within these classifiers specific values, and that for the sake of ensuring the algorithm's relevance towards the imbalanced data. That is why in the third section we are going to see what are these hyperparameters and why did we choose them. Once we have set the hyperparameters values and obtained the initial model for each classifier, we are going to move to the testing phase where we are going to calculate both of the models' relevance through a set of evaluation metrics that we're going to see in the fourth section of this presentation. Next will be the experimental results where 4 practical tools are used, 2 for each classifier. Finally, we will close this video with a conclusion where we will summarize the whole presentation and introduce this article's solution as a part of a bigger solution for future work. It all started with medical monitoring devices that is basically attached to a patient in order to monitor its vital signs. If the patient goes into a critical state, an audible alarm is triggered by the device. However, there are cases where the alarm was triggered while the patient is in a normal state. And in that case, we call it a false alarm. And if false alarms keeps getting triggered many times, it will create desensitization that comes from the medical staff. This desensitization leads to one of this behavior's consequence, and which is to completely ignore most of the alarms. And among most of these alarms, there are true alarms that must not be ignored. And if it is the case, it means we are ignoring most of the patients who are in need of urgent medical attention. That's why we are looking for a solution to reduce this high rate of false alarms. The first thing that was done was extracting medical data, and we are going to apply upon them 2 classifiers. Right after selecting the classifiers, we will estimate hyperparameters. Thanks to these hyperparameters, we obtain models that can be relevant, and that by seeing the different evaluation metrics, starting from the accuracy to the area under curve. The common thing between SVM and medical monitoring devices is that SVM is based on binary classification, and we can represent the binary class by the presence or the absence of alarms, a result generated by the medical monitoring device, and that is what creates a link between these ones and the SVM. So, binary classification is what made us think about SVM. As I said, we can have an alarm for an observation. In other words, a class value UI equal to +1, or no alarm, meaning that UI is equal to -1. And generally speaking, in SVM, there might be a linear separation or nonlinear separation. In our case, we are dealing with nonlinear separation. Theoretically speaking, in SVM we have to find the so-called optimal hyperplane, also called the hypothesis. It is the SVM model that we need for the testing phase. The hypothesis is either equal to the first equation that we are seeing here when we are dealing with linear separation, or equal to the second equation that we are seeing here. So both of these equations might be equal to h of x. However, in nonlinear separation, if the number of features is too high, then it will be impossible to calculate the hypothesis, and to solve the issue, we use what we call the kernel trick. What allows us to replace the dot products by the kernel trick is the theorem of Hilbert-Schmidt, which says that at a certain point, the dot products are equal to the kernel function. Now, for the LASVM, it is based on the same theory as the one of SVM, but with additional features, and the most important one is that it is an online classifier, meaning that it accepts new observation, even after sending a model, unlike the batch mode in SVM, that once it sets the classifier's model, it cannot be changed, and no more instances are accepted. So it is based on incremental and online learning, and LASVM is an incremental and modified version of SVM. It has other advantages like using less memory, training significantly faster, handling noisy data, and avoiding the overfitting problem. Another question is asked for LASVM. What is additional compared to SVM in terms of procedure? Imagine the following scenario. By setting the optimal hyperplane, we have what we call the support vectors. In SVM, the number of support vectors can no longer be modified, meaning the value of S we are seeing here is unchangeable, and SVM no longer accepts new example. This is not the case of LASVM because indeed it accepts new example, like an example K. And what does LASVM do to it? It inserts K into the set of support vectors, meaning it first adds K, then it inserts another example within S to find the difference tau minus violating, noted ij, and known as a pair, and we obtain along with a maximal gradient G. Then a direction search is performed. This whole operation is called process, and we perform it if a new example K comes. However, we do not execute process if the current example K is a support vector or if ij is not a tau minus violating pair. Along with process is another operation called reprocess, and its role is first to remove some elements of S following the criteria of maximum margin in SVM, then it searches the tau minus violating pair of elements of S with maximal gradient. It then performs a direction search, then removes blatant support vectors to compute at the end two quantities, which is the first one be the bias term of the decision function or the hypothesis, and the gradient delta of the most tau minus violating pair in the set of support vectors. We need both of these results to use them in the LASVM algorithms where process and reprocess are added and need to be performed to run LASVM, whose pseudocode is the following one. First, we initialize S with the set of examples quantified as support vectors, and with it we set alpha of the hypothesis to 0 and compute the initial gradient G. The most important part is the online iteration, in charge of updating the hypothesis with process and reprocess when an example or a set of examples come in, and we keep repeating reprocess until the gradient of the most tau minus violating pair in S does no longer exceed tau itself. Now, moving to the hyperparameters. They are parameters that we pass when we create our classifier, and they can make a huge difference in the hypothesis that the classifier arrives at. Let's start by the gamma. If you don't set it, basically a nonlinear model will almost look like a linear model, which means that gamma is the decision region. If this parameter is low, then the so-called curve of the decision boundary is low, meaning the decision function is broad. Next we have C, which represents the penalty of misclassifying a data point. If it is small, the classifier is tolerant with misclassified data point. But when it is large, the classifier is heavily penalized for misclassified data. Then we have the tolerance margin, noted epsilon, which has an effect on the smoothness of the SVM's response, and it affects the number of support vectors. There are other unique parameters that we can set manually, like the first three. And they are important in our case because we have imbalanced data. First, we have the class weight, which can be set to balanced if the training data is imbalanced. Practically speaking, it is available at the in the sklearn project, which means one of the tools used sklearn project for experimentation. Second and last, we have the weight, also noted W. It manually sets the weight of each class values, and if the class value have a high weight, it means that this class value needs to be more focused on in terms of support vectors. And if the weight is low, then the class will not heavily impact on the hypothesis. Let us focus on the evaluation metrics that we calculate after the testing phase. First, we have the accuracy, which simply is the rate of classification, either for independent test set or using some variation of the cross-validation. When dealing with imbalanced data, accuracy will not show the real performance of a model. That is why we call for other metrics. Second, we have the precision. It cannot have a concrete sense until it is introduced within an application domain. It is the fraction of relevant instances among the retrieved instances, meaning the ratio of the true positive observation correctly classified and all observations that are classified as positive, either they are true positive or false positive. Third, there is the recall that shows the model's real performance when imbalanced data is shown, which means that this is the most important metric among the rest. To put it simple, it is also called the sensitivity, and we can refer it as the medical staff's sensitivity towards the alarm. The higher the recall is, the more sensitive the clinicians are towards the alarms. Now, the fourth metric is the F1 score. It combines two previous metrics in order to calculate it and models accuracy in a different angle. Generally speaking, it is mostly used in binary classification, and it is a measure of how precise a binary classifier like SVM is. Nevertheless, F1 is widely used in most application areas of machine learning, not only in binary scenarios but also in multi-class cases. Last but not least, the area under curve, or AUC, tells us how much a model is capable of distinguishing between two classes. That is why it is very useful when our data is imbalanced. The higher the AUC is, the better the model is at predicting zeros as zeros and ones as ones. In the experimentation, we will focus on 4 datasets. Each dataset represents recordings of vital signs of a patient, and for each dataset we used 4 tools, 2 for SVM and 2 for LISVM. We will compare the results of the evaluation metrics for each tools. Now, starting with the first dataset, we notice here that with accuracy we cannot determine what is the best tool. The 2 important metrics here are the recall and the area under curve. The solutions using Leap SVM seems to provide the best results, where in SVM the recall is the highest, and if we want to accept, for example, new examples, we will select LISVM instead of SVM, which has a sensitivity better than the 2 first tools. As for the second dataset, we see a big difference between the rates, and this difference comes from the estimated parameters. Some of these parameters are available at certain tools, but not at other tools, and vice versa. Here, gamma was given the same value to the 4 tools, same as epsilon in the first solution on the table. And Leap SVM here provides unique parameters for the 2 last solution, which made them more relevant in terms of result. In the third dataset, we notice the same thing as in the first dataset, meaning that the metrics giving the most pertinent results are also the recall and the area under curve. However, the difference is that the first solution dominates with the highest recall, while the last solution is the best when it comes to area under curve. Nevertheless, an overall Leap SVM solution still provides the best results. Finally, in the last dataset, we can deduce that the second solution is providing the highest area under curve and the highest rate overall. But in terms of sensitivity when dealing with alarms, it is not the best tool to apply. The rest of the results are close to each other, as we can see here, for each metric, but the first solution overall gives the best rates. Now, to conclude, the SVM is known for its good generalization performance, and it can learn with low number of training examples, but on the other hand, it cannot handle data imbalance. That is why tuning hyperparameters is needed to increase the algorithm's relevance. Nevertheless, while SVM works in batch mode, this means that once the training phase is done, the parameters can no longer be changed with the generated model. In that case, we introduced one of its extended version based on the online learning, known as LISVM. The advantage of LISVM is it allows the training of new example while already having a model, and with each example coming, we update not only the model but also its parameters. However, overall, due to the given experimental results, there's a need to go for a solution that makes a whole analysis of the data in order for it to give us the optimal hyperparameter values. for the sake of outputting high rates that defines how well the learning algorithm will perform in a real example. Another point very important to mention is that this solution can be part of a bigger solution, meaning that here we can deduce that this is some kind of dynamicity in terms of observations. We can, for example, work on other solution like dynamicity over the attributes and dynamicity over the class, and then we can combine the three of them in order to obtain a complete solution that makes that makes a complete dynamicity over the three axes. And that's it. Thank you very much for your attention.